Welcome back to ECE 501B. Homework number 4, has anyone started that? It's not available, so I don't think you can start it. I need to get that posted. It's due in 8 days. I was curious how many hands I would see raise or be raised when I asked how many have started homework number 4. I think I saw some online students raising their hands. I have something going, I guess, a connection with the online students that is implicit. But a method for finding eigenvalues and eigenvectors, a sort of a mechanical way of doing that, there are some notes following Monday's lecture that deal with that process of finding eigenvalues and eigenvectors by essentially a process of elimination and back substitution. We want to continue today with chapter 5, and last time we presented the theorem 5.6, which was dealing with distinct eigenvalues and what you can obtain or what you know once you have a linear map that has, or a linear operator that has distinct eigenvalues. Then you know that you have a set of linearly independent eigenvectors associated with each of those distinct eigenvalues. We will start today after the recap with corollary 5.9, which talks about the number of distinct eigenvalues that we can have in a operator, and that's limited by the dimension of the vector space, V. Then we will talk about finite dimensional complex vector space. That's what FDCVS stands for, a finite dimensional complex vector space. If it has a dimension, if it's more than one, or if it's one or more, then that particular map has an eigenvalue. That's theorem 510. And then we will start looking at nice matrices, which are upper triangular. And we'll hopefully gain some insight into what nice matrices look like, which are representations of a linear map or these linear operations. Relative to eigenvalues and eigenvectors, so with respect to eigenvalues and eigenvectors, we have this invariant subspaces. That's what these eigenvectors represent. And those are associated with this linear operator T. And if we do have, or if this expression exists, then we call lambda the eigenvalue and we call omega the eigenvector. If that TW equal lambda W does have a solution, then that implies that we actually have that eigenvector living in a particular null space, T minus lambda I times a vector, where if that is equal to 0, then we can find this non-trivial vector W that is indeed an eigenvector, and it's associated with the specific lambda that allows this equation to be true or to hold. We stopped or finished last time with this theorem 5.6, which says that the eigenvectors associated with distinct eigenvalues, and now they're satisfying this equation, TW is equal to lambda W, those eigenvectors are linearly independent. We have a vector space of dimension 10, maybe it has 3 distinct eigenvalues, then we know that we can find at least 3 linearly independent eigenvectors in that 10-dimensional vector space. That's what that's saying. Let's pick up from that point and move forward. We proved that last time. Let's now look at corollary 5.9, or really just state this. And this says that given a linear operator T, that linear operator t cannot have more than the dimension of your underlying vector space V distinct eigenvalues. If you have a 10-dimensional vector space V and a linear map on that vector space, the linear map can have no more than 10 distinct eigenvalues. You can't have 11, you can't have 12. And one of the reasons for that, or one way to sort of think about that, is the idea of a basis. When you have a basis, what does that mean? What two properties exist for a basis? Do you remember? So they have to be spanning, these vectors, a basis, a set of basis vectors have to span the entire space, and those vectors have to be linearly independent. And you can only march up so far in terms of having vectors that are linearly independent in a finite dimensional space. If your finite dimensional space is 10 in value or in size, then you can only have 10 vectors forming a basis. And that's why you now can only have at most the number of distinct eigenvalues. The most you can have is associated with the dimension of your vector space, underlying vector space. For the proof, we won't look at that. We'll just refer you, well, we won't do it here. That's outside the classroom. So look at the textbook for the proof of that. Let's now look at another concept that we have available to us based on the fact that we are dealing with linear operators. And this is now powers, polynomials, and functions of operators. So that's the PPF of operators. Powers, polynomials, and functions of operators. And this is now playing on the idea that since an operator or what is the definition of an operator? Just the term operator, you should start thinking about what concept. It's a linear map, isn't it? But it's a special linear map. It now goes from the domain, and the codomain is the same vector space as the domain. So it maps back into itself. And so we may not have, well, in our context, we are defining, so the question was, are all operators linear? The way that we're defining the operator is it begins with a linear map. And so now a linear map being an operator, the way that we are defining operator says that now that's a linear map that takes the vector space as the domain and comes back in to itself. Since an operator is that way, since an operator is a map from a vector space back into itself, that's allowing us then to continually or repeatedly apply that operator to a vector or to the result. So we can now say repeated applications of that operator are well defined. Whatever result we get, we can use that result and apply the operator to that result. Or we can say now for t being a linear operator on this vector space V, we can define some specific notation. For example, if I now say t raised to the m power, that's now a shorthand for t applied to t applied to t Michigan times, or m times. And that makes sense because this operator maps from the input to the output, where the output is the same as the input vector space. And that can now be used as the input to the operator again. Another notation that we will use is if we now say t to the 0th power, the linear map to the 0th power, that's now defined as the identity map on that vector space, or the identity operator, I. Now that we have that, this repeated application of the operators, with this, we can define polynomials of operators. For example, if somebody gives you p of z being a sub 0 plus a1z plus on down to, let's say, a sub m z to the m, then we can actually associate with that polynomial p of z, we can now define a operator, a polynomial operator, p of capital T. In what way? We have a sub 0, that's now a scalar, but that scales t to the power 0, which we've defined to be simply the identity map, I, plus a sub 1 times t. So everywhere we had a z, or a power of z, now we can just take that many powers of our operator, t, all the way to, let's say, a sub m t to the n. And once we have polynomials of operators, now we have an even more extensive relationship or utilization that we can use for these operators t. Once we have polynomials, we can even start talking about more complicated functions of operators. For example, suppose we are given f of z, which is some function. Then we can associate f of t, we can set that equal to p of t, where p of t, or let's say where p of z is in fact the Taylor series expansion of f of z. And a very useful example can be given. Let's say we're given a linear operator t on some vector space V, and suppose that somebody says, I want to find what the operator exponential looks like. So now let's say that we have f of z equaling e to the z. That's our function that we are trying to now express in terms of powers of this operator t. What's the Taylor series of e of z? So it has all these factorials in it, doesn't it? I think I heard that come through. We have e to the z is equal to 1. Let's just write them out so we don't get lost in this factorial or just distracted by the factorial at first, plus z plus z squared over 2 factorial. Now when we get higher powers, now we start getting these factorials involved. So we now have z squared over 2 factorial plus z cubed, over 3 factorial, and that pattern is repeated. If that's the Taylor series expansion of this function, e of z, now we can use that on this linear operator, capital T. Now we can say if somebody wants to know what's the exponential of that linear operator, that maybe looks a little interesting, e to the t, but now I hope maybe you've seen that for a matrix. This is now a linear operator which has a matrix representation. That's now I plus t plus 1 over 2 factorial t squared plus 1 over 3 factorial t cubed, etc. And you may see that matrix exponential used a lot, for example, in a controls class or maybe even in quantum mechanics. So this is used heavily. Let's say in advanced topics, for example, control or quantum mechanics. Now we have, and that's now, remember how we started that section, that was powers, polynomials, functions of operators. Now you know with operators you can come up with any function you might have, and if you can now find a polynomial description for that function, you can now find the operator polynomial expression for that. So you can now find a function for your linear operator, capital T. Let's now talk about another theorem which now says that every operator on a finite dimensional complex vector space which we may at some point, and I don't even know if I want the periods in there, let me just say that that's FDCVS. Almost sounds like a drugstore. We didn't have it preceded by the fire department. But we now have a fire department CVS, or whatever that means. For every operator on a finite dimensional complex vector space, an FD CVS of some dimension, so the dimension is greater than 0, we can find an eigenvalue. And the key here is that complex. If we were not on a complex vector space, we wouldn't necessarily have an eigenvalue for that linear operator or for that operator. The fact that we have a complex vector space allows us to be able to make this statement. If it was a real vector space, you've already seen a 2 by 2 matrix that does not have real eigenvalues. So you could even have a two-dimensional space. If you're dealing with a real vector space, it may not have an eigenvalue. But here, if you're dealing in the complex vector space, you do have an eigenvalue. Let's show that or prove that. We're starting then with a complex vector space given complex vector space V with dimension of V equal to little n, where n obviously needs to be bigger than 0, and a linear operator T exists on that operator, or we have a operator on that vector space. So that's given. Now let's select or choose a vector V in that vector space capital V, and let's make sure that that vector is not the 0 vector. So V is not equal to 0. If we have that, then what can you tell me about the following list? The list V, TV, T squared V, T to the N V. If I now produce this list of vectors, we have V, TV, T squared V on up to T to the N V. The main thing now is going and putting on your programming hat and saying, how many vectors do we actually have? We have n plus 1, don't we? We're going up to T to the N, but we started with basically T to the 0 to V. So we actually have n plus 1 vectors on an n-dimensional vector space. So now what can you tell me about this list? There's some dependency here, isn't there? It has to be. So the list, V, TV up to T to the NV, must be linearly dependent. Since that list has length n plus 1, and we assume that our dimension of our vector space was n. If we now have a set of linearly dependent vectors, we can combine those with some scalars and make it equal to 0 vector if they're linearly dependent, where some of those scalars are non-zero. Thus, if we write 0 is equal to a sub 0 v plus a sub 1 tv plus dot 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 a sub n t to the n v we can actually find a set of, again, we're working on a complex vector space, so these scalars can be complex. We can find a set of complex a sub l's that are not all 0, that satisfy the above equation, or that make this equation true. Since those vectors, those n plus 1 vectors, are linearly dependent, we know this from material that we used on exam 1 or leading up to exam 1. We can now find some linear combination of those vectors that will sum to the 0 vector by the appropriate choice of these coefficients. Let's now define a new variable or a new constant, little m. Let little m, again, what are we trying to do? We're trying to show that a linear operator has at least one eigenvalue. That's our goal. Let little m be the largest integer such that a sub m is not equal to 0. And let's say we had a 4-dimensional space. Maybe a sub 4 is 0. Maybe a sub 3 is not, to form this linear combination. So little m would be 3. It doesn't have to be the dimension of our underlying space, little m. But remember what we started with. We assumed that the vector v was not equal to 0. It was a part of our vector space. So now, since that vector v is not equal to 0, and we know that this equation is true, then we know that a sub 0 could either be 0 or it's not equal to 0. Either a sub 0 is equal to 0 or a sub 0 is not equal to 0, and if it's not equal to 0, then we know that there's another non-zero value for the coefficient, a sub l. If that's the case, then we know that m is strictly bigger than 0, but maybe equal to the size of our vector space, little m. Now we have at least a linear polynomial. We have a to the m, where m is bigger than 0, so we have to have an a sub 1. That's really what we're saying here. That's guaranteed. Now let's create a polynomial based on those coefficients that we use to equate these dependent vectors to 0. We have these coefficients. They're complex. Now let's build a polynomial from those coefficients. We can use the a sub j's to write a polynomial, let's say p of z, equaling a sub 0 plus a1z plus dot 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 plus a sub n z to the n in general. If we have an nth order polynomial, what do we know about that if these coefficients are complex? Now, how well do you have Chapter 4 memorized, since we skipped over Chapter 4, or that was on you to read? Now this is this property of algebra. Now we know for an nth order polynomial, we can have roots in roots of that polynomial. So from Chapter 4, any polynomial, since we're on this complex vector field, any polynomial of order n with complex coefficients actually has little n complex roots and can be factored into little n terms. You can contrast that actually with respect to a polynomial with real coefficients on the real number line. So this is not true in general for real polynomials in general. So what we're saying is we now have P of z equaling some coefficient, complex coefficient c, and a bunch of factors, linear in this variable z. We have z minus lambda 1, z minus lambda sub 2, up to z minus lambda sub m, where m was the highest power of our, or the largest coefficient of the highest power of z that was non-zero. So we really only have m of an nth order polynomial. Meaning we might have many roots at 0, for example, depending on the difference between little m and little n. But now that we have a polynomial, now we can apply that polynomial or use our operator in this polynomial expression, or relative to this factored form of the polynomial. So let's now return to a polynomial nt. So that now we have 0 is equal to a sub 0 v plus a sub 1 tv plus a sub 2 t v squared, etc., plus dot 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 plus a sub n t to the n v. So now we're returning, I maybe was misleading in my discussion. Let's just rewrite this polynomial here. So now we know this, we found complex coefficients that allow this expression, this polynomial in our operator t, to be 0. Let's now just go back to that for now. Now that we've sort of found a polynomial in z based on these same coefficients, we've created this polynomial. We factored that by the realization from chapter 4 that an nth order polynomial has n complex roots. In this case, we knew that we really only had little m of those, but now let's go back to this polynomial and show what it will equal. Meaning, we now have this relationship via additivity What am I doing? I'm putting my square in the wrong place. So let's go back here and get rid of that square and say that this is now t squared. So that was our polynomial from here. Maybe I messed up because I didn't include it here. I had a sub 2 t squared v. Because we had v, tv, t squared v, etc. We said that, oh, we have n plus 1 vectors. We can form we can sum those up with complex scalars to create the zero vector. Let's now return to that polynomial, and via additivity we can actually factor out that common v from all of these terms, or from the terms in this sum. Meaning now we can say that that's equal to a sub 0 I plus a1t plus a sub 2 t squared plus a sub n t to the n v. And now we can compare that with this, p of z. This is really p of t. If you look at what's in parentheses and compare that with this p of z, we've now simply replaced z with our operator t in that parenthetical relationship. But now that we have that, and we know that we can actually factor p of z into this expression by our linear, or by our algebra, that any complex coefficient polynomial of order n has n roots. Now we can do the same thing for our polynomial in this operator t. Meaning, now we can factor that and say that we now have 0 is c times z minus lambda 1I, but that's just t minus lambda 1I, t minus lambda sub 2I, t minus lambda sub mi times v. And what does that mean? That means that one of those factors has to map to 0. Since it's 0 is equal to that product of factors, we now know that t minus, let's say, lambda sub ji times v maps to the 0 vector for at least one lambda sub j. And that's what we were setting out to show, that we had at least one eigenvalue for a operator on a finite dimensional complex vector space. Now we have shown that we do indeed have that, since if we have a lambda sub j that satisfies this expression, we've called that an eigenvalue. And that's what we were setting out to show. So that we now have the conclusion that we were wanting to find. Therefore, T, this operator, has at least one eigenvalue. And that's what we were trying to show. Meaning we were saying if you have an operator on a finite dimensional complex vector space, you know that you have at least one eigenvalue. And we showed that by really working with linear dependent vectors, finding coefficients, scalar coefficients that are complex that you can sum to 0, then knowing that you have some nth order polynomial, knowing this algebra fact that you can factor that, we can then relate that polynomial that we started with in Z to this polynomial in our operator T, and then conclude that that is factorable, just like the polynomial was factorable. And if that right-hand side is equal to 0, then one of those factors times V has to be 0. At least one of those. And that now says that we can find an eigenvalue when we're dealing with an operator on a finite dimensional complex vector space. Now that we have these ideas of eigenvalues and eigenvectors, let's see if we can make those maybe look a little easier, or maybe produce matrices or maps that are not as dense or as involved as what they could be generically. And to do that, let's start looking at a particular structure on a matrix, which we'll look at then upper triangular matrices. And before we get too into this, what can we say about the matrix representation of an operator? What do we know about its dimensions, or in terms of its shape? It's square, isn't it? So we know that these operators, or the matrix representation of these operators, are square. And we only really need to worry about one basis set. We could have many, but as long as we have one, then we should be okay. Only need to specify one basis. Once we have a basis and the idea that this matrix representation is square, what we're looking for is some good or a nice, efficient set or a basis. And what that means is we might want the matrix representation to not have very many non-zero terms in it, which is where the upper triangular comes from. What we're doing is we're looking now to find good or efficient bases for the system, or really the operator. And the claim is that a good basis is one where the matrix representation of this operator is simple. And now we need to define simple, since I put it in quotes. But we want a good basis will be one where the operator, this is some linear map from a vector space back into itself. We now want to have the matrix representation of that operator simple, whatever that means. The meaning that we are going to imply by simple is that we want our matrix representation to have lots of zeros. That's what we're shooting for. A matrix representation that has a lot of zeros, and one matrix representation that has a lot of zeros is a structure that below the diagonal will all be zero. That's a good or a simple matrix representation of a linear operator. So now let's see what we can come up with relative to that. The results that we've already been working with. So the results we've already developed are sufficient to show that for a finite dimensional complex vector space, there is a basis where the representation of T is this matrix representation of the linear operator capital T is now lambda 0, everything else below that lambda is 0 in that column, and then we haven't yet decided what's to the right of that matrix representation, but we do know, so this star is meaning what are in those remaining, let's say n minus 1 columns, can be arbitrary. But at least we can guarantee that everything below the 1, 1 entry in that matrix representation is going to be all 0. Now, where did that come from if it's already from previous results? Here's sort of a proof of that idea. One is we've previously proved that T has at least one eigenvalue. And let's call it lambda. And an associated eigenvector, let's call that V. We've also been able to, or we've also shown that once we have a vector we can augment that vector or add to that vector more vectors or extend that vector to form a basis by creating more linearly independent vectors that will span the space. We've previously proved that we can always extend a linearly independent list of vectors into a basis. So what we want to do then is extend from V to fill out our number of vectors that we need to form a basis for this finite dimensional complex vector space. So let's extend V, let's say this list V, to a basis on the finite dimensional complex vector space. If we do that, in this case, then, the matrix representation of this linear map T, remember how we built that up? If we looked at the matrix representation, we might have said this is now A sub 1, 1, A sub 2, 1, dot, 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 A sub n 1. Remember that notation that we were using? And what did each of those A's mean? That was now how this linear map would be represented in terms of the basis vectors. And now our first basis vector is V1. We now say that this linear map applied to V needs to be represented in terms of V and this extended basis. If that's the case and V is an eigenvector, what do we know about those A's? Meaning, we are now thinking about this matrix representation being something like, we now have V, let's say W1, W2, W sub n minus 1, and now we have an A11, an A21, an AN1, we have an A21, an A22, an AN2, and these are all supposed to be such that the first one is TV, the next one is TW1, etc. And this last one, let's say, is TW sub n minus 1. But how did we, or what do we know about TV? TV was V was an eigenvector, wasn't it? Because we said we can find at least one eigenvalue for this operator T. And now we've assigned that one eigenvalue, or I'm sorry, we can find one eigenvalue for this operator T. The one eigenvalue we said is lambda. And we found an eigenvector V. We said the eigenvector associated with lambda is V. And now I'm saying here we are, we have TV equaling some linear combination of these basis vectors. And we need to combine those using this first column of A's. What does that mean? Here this would be, let's say, A sub n, or I'm sorry, a sub 1n down to a sub nn. What do we know about that first column? If v is an eigenvector and we're trying to represent TV in terms of v and this rest of the set of basis vectors. A11 is lambda, isn't it? It's only going to be in that direction since v was the eigenvector, and all the other a's are 0. Meaning in this case, we can now say that the matrix representation of T can be written as lambda 0, 0, everything else 0, and for now, let's not worry about what's in the next n minus 1 columns. And we can do that because of what we were just showing up here for the way that we were expressing this TV, then TW1, etc., in terms of a linear combination of the basis vectors. Remember, the kth column of this matrix representation is the result of applying T to the kth basis vector. And in our case, we were using little k to be the first vector. Our first vector was chosen to be the eigenvector. Our first vector is the eigenvector v and we could write that as v is equal to some linear combination of v w1 plus something w2, etc., plus something w sub n minus 1. These are now our extended vectors that create this set of basis. Obviously, then, v is just 1 times itself and 0 times all the other basis vectors. And because we were using TV was the eigenvector associated with that one eigenvalue lambda that we said we knew existed for some operator T, then we know that we can at least zero out everything below the top coordinate in our matrix representation of this linear map T. We know we can at least do that, and that's now giving us a lot of zeros. What's nice is we can actually do better than this. We're actually going to show that we can start to zero out everything below the diagonal. But we can do even better. An upper triangular matrix is one where all of the elements below the diagonal are 0. Meaning if we wanted an upper triangular matrix, we could have lambda 1, lambda sub 2, all the way down to, let's say, lambda sub n. We may have some non-zero entries above that, but everything below is 0. Let's now look at an example of an upper triangular matrix and just get some insight into what that means. Let's now look at a particular upper triangular matrix where suppose now this operator T is in 3 space, real 3-dimensional space. For our example, suppose that the matrix representation of a linear map T is what we'll call A, and let's say now that that T is going to be using the standard basis. Let's say that we now have in 3-dimensional space the V, let's say this is V1, V2, and V sub 3. This is our standard basis. And let's say that that matrix A is now 2, 0, 0 in the first column, 3, 4, 0 in the second column, and minus 1, 1, 5 in the third column. Let's say that's the matrix representation of some linear map, capital T. Let's now look at what that means in terms of eigenvalues and eigenvectors. If we look at the eigenvalue-eigenvector equation, that now is AX is equal to lambda X, or that says A minus lambda I times X is equal to 0. And another way of thinking of that is this eigenvector X is now in the null space of this matrix A minus lambda I. And what are our eigenvalues for that matrix? This is our matrix. Have we talked about eigenvalues and special matrices? Thought we did. What do we know about eigenvalues and triangular matrices? What if we had a diagonal matrix? What would you say the eigenvalues were? If you had a diagonal matrix. Let's say you had 1, 2, 3 on the diagonal of a 3 by 3 matrix. What were the eigenvalues? 1, 2, 3. If we have a triangular matrix, the eigenvalues are still on the diagonal. Here we have an upper triangular matrix. The eigenvalues in this case are 2, 4, and 5. So now we know what the eigenvalues are. We can use those to try to find the eigenvectors. The eigenvalues are on the diagonal. Not only for an upper triangular matrix, but also a lower triangular matrix, or even a diagonal matrix, the eigenvalues are on the diagonal. But in this case, then, we have eigenvalues. Let's say lambda sub 1 is 2, lambda sub 2 is 4, and lambda sub 2 is 5. And if we want to now compute this matrix A minus lambda I, we now simply subtract lambda off the diagonal of our upper triangular matrix. We now have 2 minus lambda, 0, 0. We had 3, I believe, in the 1, 2 entry, and then we have 4 minus lambda, 0, and then we had minus 1, 1, and then our last entry in the 3, 3 space was 5, and we subtract lambda from that. That's now our A minus lambda I matrix. We want to look at all three of these different eigenvalues. They're distinct, so we would expect what from our results or from earlier theorems? We have distinct eigenvalues. We would expect linearly independent eigenvectors. So we now will be able to find 3 linearly independent eigenvectors. We have 3 linearly independent eigenvectors in a 3-dimensional space. We can use those vectors as a set of basis vectors if we wanted. Let's now find those eigenvectors. If we look at now the case for lambda equal 2, we want to now try to find the vector that's in the null space of A minus lambda sub I with lambda equal to 2. That's what we're looking for. If we now evaluate this A minus lambda I matrix for one of the eigenvalues, which in this case, let's look at lambda equal to 2, now we have the following matrix. Plugging that in, we have 0, 0, 0 in the first column. In the middle column, we have 3, then we have 4 minus 2, or 2 and 0. And in the third column, we have minus 1, 1, and 5 minus 2, or 3. And we want to find a non-zero matrix, X, which we will parameterize as x1, x2, and x3, that satisfies that matrix times x equals 0, or that vector x is in the null space of this matrix that we now have when lambda is equal to 2. And you expect to see a non-zero vector x in this matrix multiplication just by looking at your matrix. What do you see? How many linearly independent rows are there in this matrix? Or how many linearly independent columns are there in this matrix? 2, right? So we would expect, since we have a 3-dimensional matrix, or a 3 by 3 matrix, and we only have 2 linearly independent rows or columns, we should be able to find a non-trivial vector that can combine those 2 columns to form the 0 vector. That's what we have learned is available to us by means of having linearly dependent vectors. If we look at the third row, meaning now we're going to sort of start at the bottom and work our way back. If we look at the third row in terms of what that produces for an equation, we see that we get 3x sub 3 must equal 0. Well, that now imposes a particular value for x sub 3. In order to solve that equation, x sub 3 is forced to be 0. What do we learn from the second row? The second row says we have 2x sub 2 plus x sub 3 is equal to 0. But we've already learned that x sub 3 was 0. So now we know 2x sub 2 is 0, or x sub 2 is 0. From the first row, now we have 0x1 plus 3x2 minus x sub 3 equaling 0. But from the earlier 2, we already know x3 is 0, x2 is 0. Now we have 0 times x1. What can x1 equal? x1 could equal 0. We want it to be non-trivial, though, don't we? So it can be anything, can't it? x1 could be anything and satisfy this matrix times x1, 0, 0. We've now forced the last two coordinates to be 0 by this relationship of the a minus lambda I, and now we can say that x1 can actually be anything. And if it can be anything, let's just let it be something that's fairly easy to keep track of. So now, for the eigenvalue 2, lambda sub 1 equal 2, we know that the associated eigenvector is in the direction of 1, 0, 0, letting x sub 1 be something nice, which 1 is nice. It could be anything as long as it's a non-zero x sub 1 coordinate, and x sub 2 and x sub 3 are forced to be 0. What do we know about the eigenvector associated with the eigenvalue 4? Now we want to look at a minus lambda I with lambda equal to 4. If we plug that in, we now have 2 minus 4, or minus 2, 0, 0. We have 3, 4 minus 4, or 0. And then in the last column, we have minus 1, 1, and we have 5 minus 4, or 1. And we now have an x1, x2, x3 equaling 0. Now, how many linearly independent rows do we have here? Not that we need to know necessarily, but we are going to be able to find we have 2 dependent rows, don't we? The last 2 are exactly the same. So now this tells us, like we learned before, if we look at the third or second row, that's forcing the third component to equal 0. Then from the first row, we can see that we have minus 2x1 plus 3x sub 2 minus x sub 3 must equal 0. But we've just learned that x sub 3 is 0, so that now we can just pick a convenient value for x sub 2 and solve for x1 from this relationship. Suppose we now say with x sub 2 equal to 2, since I want to have nice integer values in my vector, if x sub 2 is 2, that now says that 2x1 is 3x sub 2, or 2x1 is 6, x sub 1 is now 3. So that now for lambda sub 2 equal to 4, the eigenvector associated with that is in the direction of 3, 2, and not 1. We're not counting down properly. This is 3, 2, 0. That's now the structure of our second eigenvector. And has anybody already built the third eigenvector? I'll give you the answer and you can verify it tonight. With lambda sub 3 equal to 5, that will give you a direction for the eigenvector that is 2, 3, and 3. And I hope that it's clear that W sub 3, it has a non-zero third coordinate. W sub 2 has a 0 third coordinate, and W1 has 0 coordinates for 2 and 3. Those three vectors are linearly independent. And now we have a way of forming a basis for this linear map that was associated with the matrix representation that was upper triangular. We'll pick up at that point next time, but we're really trying to find simple matrix representations of linear operators, and that's now giving us this upper triangular structure.